Okay, what's up guys? So today we're going to jump into our hydrocarbon reactions and we're going to start with alkane halogenation. Okay, so halogenation is a light or heat initiated substitution reaction where a chlorine or bromine is going to replace a hydrogen on an alkane type carbon. So that means this has to be a carbon with only single bonds. So what do I mean by light or heat initiated? That means that we need either light or heat to catalyze this reaction. So given this definition, I want you to go ahead and pause the video and see if you can draw the products for both of these reactions and name your organic products for both of these reactions. Okay, so this first reaction, we are reacting a chlorine molecule with a methane molecule in the presence of a light catalyst. So in this substitution reaction, we're essentially just going to swap places with one of the chlorines in our Cl2 and one of the hydrogens on our methane, and we should get something that looks like this. So you should end up with chloromethane as your organic product and hydrochloric acid. Okay, so what about this bottom reaction? So the same thing here, we're just going to swap one of the bromines from our Br2 with one of the hydrogens on our ethane. So your product should look something like this. And the name of this product is bromoethane. And we also produce hydrobromic acid. Okay, so in both of the previous examples, we were using a short chain hydrocarbon, where it doesn't really matter which hydrogen we replace because we're going to end up with the same product regardless of which one we replace. So what about a longer hydrocarbon chain, one that has more than 2 carbons? Which hydrogen would you replace in the reaction on this slide? So the answer is it can be any of them, but we're only going to substitute one chlorine for every Cl2 reactant. So that means in the reaction below, we can't add both of these chlorines to our butane molecule. One of them has to react with a hydrogen to form hydrochloric acid. So there are 2 different organic products that can be produced by this reaction. So what I want you to do now is pause this video and see if you can come up with both of those possible products. Okay, so the strategy for answering a question like this is to figure out how many unique hydrogens our hydrocarbon reactant has. So we have 10 total hydrogens here. 6 of them are bound to terminal carbons, and 4 of them are bound to the carbons next to the terminal carbons. So that tells us there are 2 unique spots where we could substitute a chlorine for a hydrogen. We could substitute a chlorine for a hydrogen at one of the terminal carbons, or we could substitute a chlorine for a hydrogen at one of the 2 middle carbons. So the product of this reaction would be a mix of these 2 constitutional isomers. And if you haven't already, go ahead and pause the video and see if you can come up with names for our 2 possible organic products. Okay, so this one on the left is 1-chlorobutane, and this one on the right is 2-chlorobutane. Okay, our next hydrocarbon reaction is the aromatic substitution reaction. This is an iron or iron halide initiated substitution reaction where a chlorine or bromine replaces a hydrogen on an aromatic carbon. So given that definition, go ahead and pause the video and see if you can come up with the organic product of this reaction. Okay, so just like the previous reaction, we're just going to swap one of the bromines from our Br2 for one of the hydrogens attached to an aromatic carbon. So your final organic product should look something like this, and we're also going to produce hydrobromic acid. Okay, if you haven't already, go ahead and pause the video again and see if you can give me a name for our organic product. So the name of our product is bromobenzene. Okay, so to wrap today up, we're going to try a few examples. Okay, so what I want you to do now is pause this video, and I want you to name our organic reactant and draw and name every possible organic product this reaction could produce. Okay, so let's see what you came up with. So the name of our reactant is 1,4-dimethylbenzene, or you could also name this using the OMP nomenclature as paraxylene. Okay, and just like the previous reaction, we want to figure out how many unique aromatic carbons this molecule has. Okay, so what can we say about each of the carbons on our reactant? So let's start with the carbons that are not an option for substitution. So these 4 carbons right here are not options. These 2 right here aren't options because they are not aromatic carbons. What about these 2? These 2 carbons aren't options because there's no hydrogens attached to either of these carbons. Therefore, we can't perform a substitution reaction there. So that gives us 4 carbons where we could substitute a chlorine for a hydrogen. All 4 of these carbons are directly next to a substituted aromatic carbon and 2 carbons away from the other aromatic substituted carbon. So regardless of which one of these carbons we choose, the name of our product is going to be 2-chloro-1,4-dimethylbenzene. Okay, so one last example before we wrap up today. So let's react this aromatic compound with Br2 in the presence of iron 3 bromide. So go ahead and pause this video and see if you can name the reactant and draw every possible organic product this reaction can produce. Okay, let's see what you came up with. So just like in the previous reaction, we want to find every unique aromatic carbon where substitution can occur. So we can't have aromatic substitution happen at these 2 carbons because they are not aromatic carbons. These are alkane type carbons. We can't have substitution occur at these 2 carbons because there are no hydrogens attached to these carbons. So that leaves us with 4 places on this aromatic ring where substitution could occur. So how many of these aromatic carbons are unique? So let's see if we can describe these 4 aromatic carbons. So this carbon right here can be described as the only aromatic carbon between our 2 substituents. This aromatic carbon is the only one that is 2 carbons away from both substituted carbons. And then our 2 remaining carbons are each right next to a substituted carbon and 3 carbons away from the other substituted carbon. So that means we have 3 unique spots on this aromatic compound where we can substitute a bromine for a hydrogen. So we can substitute a bromine for a hydrogen at the aromatic carbon between the substituents, across from the substituents, or at the carbon immediately next to only one of these substituents. So if you haven't already, go ahead and pause this video and see if you can name all 3 of our possible organic products. Okay, so our top product is 2-bromo-1,3-dimethylbenzene. The middle product is 1-bromo-3,5-dimethylbenzene. And our bottom product is 1-bromo-2,4-dimethylbenzene.